This is part one of a three-part lecture that is a follow-up to Tuesday's lecture number 3 on chapter 2, fluid statics. Here we're going to look at chapter 1.9 just briefly to look at surface tension and capillary forces and how they may or may not affect manometers. Then we'll move to fluid statics in earnest, and we'll look at submerged forces, their magnitude and their location, the resultant forces of pressures on submerged flat surfaces. And then we'll look at curved surfaces, which take a little bit more of a specialized treatment. So let's first look at these capillary tubes and how they may or may not affect manometers. Then part 2, flat surfaces. Part 3, curved surfaces. So here's a capillary tube, a thin, let's think of glass tube, put in fluid, and the fluid, as you know, will rise up in that tube. You probably remember this from your physics class. It will rise to a level H, and then it will stop. There, the forces that are drawing the fluid up the tube will be in equilibrium with the weight of that water that's moved up the tube. Surface tension is a result of molecular forces between the fluid molecules and other molecules, either a solid surface or in some cases other fluids if you have a fluid-fluid interface. But here it would be the solid surface, the glass tube, that's drawing the fluid up there. So we have this sort of pulling or stretching force that's caused a meniscus form when the fluid is in the narrow tube. So if you kind of turn this parabola around, you'd see kind of a cupped meniscus on this tube. So this net force here is called a capillary force, named after the thin tube. It's a capillary tube. Right here, this guy. So capillary forces can actually be positive or negative, and they could make a fluid rise or fall. Here it's shown as rising, obviously. So the rise stops when it reaches static equilibrium, as I said, when the weight of the fluid is equal to the capillary force drawing it up. So here is what happens. We have on the left-hand side. Here's just the geometrical weight. We have pi r squared. That's the area of the meniscus. The height is the h that has gone up, and rho g is is gamma. Rho g equals gamma, so that's the specific weight of the water that's drawn up. This is basically the weight of the fluid. And that is equal to the capillary force. Capillary force is given by the length of the fluid that's in contact, and that's the circumference of the circle in the meniscus that's touching the glass, and then the surface tension and the contact angle. So there's the left-hand side, the weight of the water, right-hand side, the capillary force. Density times gravity is the specific weight. Radius of the tube is very important, and then the height that it rises. Surface tension, strange units, but it's force per length. Force per length. So we take that times a length term, like the circumference here, 2 pi r, and we'll get a force. The contact angle is an interesting property. It's a property of both the fluid and the surface, so you think of it being a little different if you had water on glass versus water on concrete, or gasoline on steel, these sorts of things. You need the combination. Turns out it's about 0. It's a very flat interface. So right here, that theta, that angle, gets very flat for water on clean glass. In contrast, it's 130 degrees for mercury, which translates more to a meniscus that looks like so, and is actually depressing down relative to the water around it. This would be the case for mercury. And there you have a drawing of it. How much will it rise or fall? Well, if you just rearrange those equations, you see that you can get H right here. That's the capillary rise, and it's a function of the surface tension and the contact angle, fluid and its density, And then the key here is how skinny or fat is the tube. So it really depends mainly on the diameter or the radius of the tube, because once you've picked the fluid and the material, those parameters are set. So for example, if we had a water and glass at 20 degrees C, if you had a 0.1 millimeter thin capillary, so a pretty thin tube, you'd get a very high rise, about 15 centimeters. If you open it up to be a tube about 1 millimeter, you'd only get about 1.5 centimeters. And if you had a 10 millimeter or 1 centimeter wide tube, you'd get about a 1.5 millimeter rise. So it's very, very dependent on the diameter. You have to have a pretty thin diameter to get appreciable rises. So keep in mind these types of numbers will change with different fluids, different materials of the tubing, and also with temperature. So that brings to mind some designs. We like to think about designing as engineers. And so if you're designing based on surface tension and capillary forces, think about thermometers. How would you design one? You may not remember these, but they used to have mercury thermometers, even the kinds of thermometers we'd use when you were ill to check your temperature. They'd put in your mouth and read the thermometer. Now they have digital ones, of course, with thermistors. But here in this type of thermometer, you have this bottom reservoir full of mercury. And this mercury can rise up into this column. In fact, it has some in there already. And it's calibrated or made to the right diameter of the column. So if you can think about it, how would the mercury's surface tension change with temperature and enable it to squeeze further up the tube or drop down into the tube? It has to be made very carefully. So it's interesting to think about how to design something like that. So manometers. Manometers, as we know, are fluid-based pressure measurement devices. So here's a manometer. We have some pressure P on one side. Over here, we have atmospheric pressure. We usually put down as P naught on the other side. And so if pressure is greater than atmospheric, it will push down, and this fluid will rise. It will go down on one side and up on the other side. And from this H, then, we'll be able to determine what this pressure was over here. So they involve fluids and tubes. Tubes are somewhat like capillaries. Most of the time, though, the diameter of this tube are pretty big. We talked on the previous slide about being 1 centimeter and not seeing too much capillary rise, a little bit. So these may be even more than 1 centimeter. And if that's the case, and as we're talking about water-like fluids, it'll probably be neglected in terms of how much the capillary effect changes this distance H that we're worried about right in here. So it's generally just taken for granted in these types of problems with manometers, unless it says so, or there's a very thin radius on the capillary tubing. You can kind of ignore capillary rise and just go with the distance being caused by the pressure. So that's the end of part 1, and you can now move to part 2.